So a quick explanation on how to solve some of these little block diagrams related to faulting. So in the homework, you had 6 different block diagrams to evaluate. Now the key here is you always want to make sure you're aware of what view you have. And so cross-section view would be the side view, right? So that's the kind of slicing into a cake and looking at the layers of the cake, or maybe like looking at a road cut as you drive down the freeway. And so, and this side view is important because when we have a side view, we can identify what are called dip slip faults. Those are either normal or reverse faults. And the reason that we want to distinguish between those is because they have different stress types and they occur at different locations. So, how do we do that? Well, once we realize we're in a cross-section view, we know we have 2 choices, normal or reverse. And so the definition is really based on what's called the hanging wall. And that is the block, because we can see that the fault creates 2 blocks. We're going to argue that the hanging wall is the block that's on top or hanging above the other block. And usually there's a bunch of methods you can use to try to identify those. But the easiest, I think, is to, no matter what kind of angle this is at, it doesn't matter if it's steep or shallow or dipping one way or the other. If you place your finger on the fault and go straight up, you will always be in the hanging wall block. And so for this diagram here, this line is the fault. I put my hand or finger on the fault and I go straight up. This is the hanging wall. And by definition, when the hanging wall moves down relative to the other block, which we're calling the foot wall, that's a normal fault. And so how do we know that? Well, this is a layer that's been offset, and relative to this side, this hanging wall block has moved down. So that would make this a normal fault. And so normal fault is associated with tensional stresses. So when we jump over to this block here, you can see that, okay, so the fault angle has changed, but we still employ the same method here. We put our finger on the fault plane and go straight up. This is the hanging wall, and it has moved down relative to the other, which is the foot wall. It's still a normal fault. And so don't let the angle fool you. Just kind of do that same method. Identify the hanging wall. Down is normal. And so if we go to this other one here, we put our hand, finger, whatever on the fault plane, go straight up. This is the hanging wall. This time it has moved up. Up means it's a reverse fault, and reverse faults are usually caused by compressional stresses. If we move over to number 4 here, the view here gives away what fault we have, because in this class we're really only interested in identifying reverse, normal, and strike slip. So in map view, which is we're looking down on the surface of the earth, we have a difficult time seeing vertical motion up and down, but we can see horizontal motion fairly easily. And so in this case, there's movement along a layer or a feature here. But the fact that it says map view is kind of the telltale sign. This is a strike slip fault. And of course, shear stress is associated with strike slip faults. So we can just continue this game, right? So if it's cross section, oh, I know I have a side view. It's normal or reverse. I put my hand or finger on the fault and I go straight up. Hanging wall has gone up. That's a reverse fault. And of course, the idea of a map view should instantly tell you that that's a strike slip fault. For the folds, you have to remember a couple things, of course. You have to know what a strike and dip symbol means and the orientation of what it represents. And so in this idea here, map view, we're looking down on the surface of the earth. These are different layers of rock that are exposed at the surface of the earth. And this symbol with the short line pointing away from the middle tells you that the layers are dipping away from the center. So they're forming kind of an A shape. So this would be an anticline. And we're going to argue that most of the folds that we see are caused by compressional stresses. So whether we have an anticline or a syncline, it'd still be considered a compressional stress that would create these folds. Another way we can identify anticlines, synclines, folds is by the age of the units. And so with 1 being the oldest, 1 in the center or oldest in the center, an exposed surface like this suggests that it is an anticline because we have old units in the center, because when we crushed it and folded it into this A shape, we eroded some of the units and exposed the old rocks in the middle. So the age of the rocks can tell you what you have. This is also an anticline. In a cross-sectional view, a side view, this is usually the easiest to identify anticlines from synclines because our anticlines have kind of this A shape or anthill shape, and a syncline has kind of a sink shape or a smile shape. And so in a side view, just like when we're talking about faults, we're looking at the layers of the cake here. This shape here tells us it's an anticline. So all 3 of these are anticlines, and also we would argue that they all were formed by compressional stresses. This one's a little tricky, but because it's a map view, and in the middle of the fold is the youngest rocks, because 1 is the oldest, so 4 is the youngest. Just like this one, except that it's not parallel, it's a tilted fold. But this would suggest that this is either a syncline or some type of basin because it has young in the center. Still argue that it's compressional stresses causing this. This circular pattern that you see is indicative of either a basin or a dome. So kind of a 3-dimensional anticline would be a dome, a 3-dimensional syncline would be a basin. And because the strike and dip symbols tell you that the beds are tilted down toward the middle, right? That kind of gives us this sink shape or a basin. So this would be a basin from compressional stresses. And this one, of course, I threw in there just to annoy you, but what this is the ages are showing that there's old here, young here. You really don't have enough information to specifically identify what it is. It could be the limb, right? The side part of a syncline or an anticline. And so any fold will do if you're trying to tell me what this is. It could be a syncline, could be an anticline, could even be a monocline. So I'd take any answer for that. And of course, the stress would still be compression. So we'd argue that compressional stresses is forming all of these. You just have to remember how you identify the folds in map view. It's either the tilt of the beds, what direction they're tilting, toward the center or away. For ages, old in the center or young in the center tells us. And then, of course, in cross-sectional view, just the shape would tell us that. Okay, hopefully that clears up some things and helps you understand what was going on in the homework. If you have any other questions, you can reach out to me. Thanks.